H.323 multiplexing. Today we are going to talk about the scheme for the header compression, which we had in fact introduced in the last class, and subsequently as a result of the header compression, what kind of bandwidth efficiency one can achieve by using the H.323 multiplexing. So, this is what we are going to discuss, and before we take up the topic, just a very quick brush up with what we were doing last time. Now, the essential idea behind the H.323 multiplexing was that there we will be using a multiplexer where several sources may be able to communicate with the destinations in a simultaneous manner and in a time multiplexed manner. The advantage that we are looking for in this is a kind of a bandwidth efficiency, in the sense that instead of using the individual headers which come from the different RTP streams which are associated with the individual source ports, okay, we will be using the multiplexing where before we transmit the multiplexed bit stream, okay, through the wide area network over again the UDP RTP packet, there what we have to do is to form the packet header, okay, in a manner that is efficient. That means to say that we would like to avoid the redundant information that goes with the packet headers. The redundant information comes in the sense that for some particular streams, okay, when a session has been established between one channel with one of the destination nodes, when a session has started, then for a session we had find that there are certain fields in the UDP RTP header which remains the same, okay, and there are some fields which go through the constant increments like the timestamp, the sequence numbers, okay, those will go through some constant increments. Now, because there are some constant fields and for some of the fields there are constant increments, that is the reason why one can go through some amount of header compression, whereby when we are multiplexing the streams into one, there the mini headers that we form for every stream, okay, for every source destination combination, when we have a stream, there we will be having the header information which is there in a compressed form. And what I have described is that there are three types of mini headers which are possible. One is the uncompressed mode, in which case we will be having the full RTP header, okay. In fact, somebody was asking me that what is the composition of these 4 bits. Basically, there are 3 different types of mini headers, okay, 3 types of mini headers. So, meaning that what type of mini header it is, that is indicated by 2 bits, okay, type is indicated by 2 bits, and there are other 2 bits which are referred to as the S bit and the M bit. S bit stands for the status bit, and in fact it informs the status of the bit rate of the codec, means the assuming that codec goes through 2 different bit rates, okay. So, which bit rate it is, that will be indicated by this S bit, okay, and M bit stands for the marker bit. The marker bit is 1 when the first when any session starts, okay, the first packet would contain the M bit as 1 and the subsequent packets will contain the M bit as 0. Okay. So, the status and the marker bits, so 2 bits for the header information, okay, and 2 bits for the status and the marker. Okay. So, this will form a 4 bit field, and then we will be having a 4 bit sequence number and an 8 bit CID, which is the context ID, and this is the context sequence number, and in the uncompressed mini header the full RTP header will go. Okay. So, as you understand that initially we have to send the full RTP header, because then the demultiplexer will not be having any information about the fields which the multiplexer is using. Okay. The second type of mini header we talked about is what is called as the synchronization mini header, where the complete mini header is not given. Okay, the complete RTP header is not given, but other than this 4 bit field, that means to say the type number and the S bit and the M bit. Okay. So, T1 and T2 are the type number, that what type of mini header it is. So, if you let us say put 00 for the uncompressed, you will be putting another one, maybe 01 for the synchronization mini header. The C sequence and the CID remains as it is, but you have to add the extra R sequence and R time. So, from time to time one has to send this synchronization mini headers. Okay. This will not be avoidable, but most of the times what we want to do is to go through a third type of mini header, which we will be calling as the compressed mini header. In the case of compressed mini header, it is just a 2 byte mini header. Fully compressed mini header only has got 2 bytes, and the first byte that contains the usual 4 bit information like the type T1 and T2, where we can use say 1 and 0 combination, and then the S bit and the M bit. Okay. And then the C sequence, okay, which will be 4 bits, and then the CID, the context ID, because normally I mean when the receiver and when the multiplexer and the demultiplexer, they are having a perfect understanding, then the CID itself should be good enough, okay, in order to identify the packet. Okay. So, CID should be CID and C sequence should be enough of information. We do not require the entire RTP header streams that is required. So, that is the factor that really contributes to the header compression. And I was telling you that how with the help of this C sequence and CID we can identify the channel. It's like this, that it maintains, the multiplexer demultiplexer system that maintains one channel table in the multiplexer demultiplexer, and the channel table is identified by this channel ID. So, each multiplexer and demultiplexer combination, okay, demultiplexer of course with the demultiplexer port number. So, each multiplexed and demultiplexed combination would have a unique channel ID, and for every channel ID there will be a context mapping table like this in the multiplexer. The multiplexer's context ID table for a particular channel ID will contain these fields which I discussed last time. Okay. The source IP and the port, then the RTP's own identification, then the context ID, the payload type, etc. But what is important is that in the last synchronization, means when the last synchronization mini header was sent, okay, that time along with this whatever C sequence number was sent and whatever RTP synchronization number was sent, RTP sequence number was sent, and whatever was the timestamp, all this information, okay, remains stored in the context mapping table for that particular channel ID. Now, this is the context mapping table which gets stored in the multiplexer. So, what the multiplexer does is that when the multiplexer receives, I mean at its input, when the multiplexer receives a voice packet, okay, that time it identifies the source, because it knows, I mean when the RTP packet comes from the source to the multiplexer, the actual source to the multiplexer, that time it identifies the source with its IP address, okay, and there will be for every session a unique CID, context ID is assigned. So using the source number and the CID, it is able to identify the stream, and from that it will be able to know that for the last synchronization what was the C sequence number, RTP sequence number, timestamp, etc. Okay. Because all that the multiplexer will do now is that after identifying the source, okay, and it also knows the destination, because when it goes to this table using the channel ID, it can find out that what is the demultiplexing IP and port. So it knows that where it is to be sent, okay, and it knows and it can form the C sequence value, because as it is, when it is receiving the packet, I mean the voice packet from the actual source, it has got the RTP sequence number, not the context sequence number. But using this table, it can form the context sequence, and then the context sequence could be sent, context sequence and the context ID could then be dispatched to the demultiplexer to the proper port, which it can find out from this channel table. Now once the demultiplexer receives it, then the demultiplexer has to consult a very similar context mapping table which goes like this. Okay. So context mapping table for demux goes like this. Mapping table, and this table is also for a particular channel ID, for a channel ID in the demux. So in demux it has got these fields. We won't be concerned with all the fields actually. The CID, this is the essential field which has to be there, and then for the demultiplexer there has to be the destination IP and the port address, okay. Then the active size, then the idle size, etc. Whatever are there in the multiplexer table, that is there here also. There is a field called time difference. Actually, because in the compressed mini header the actual timestamp is not sent. So please note that this is one big change, that whereas in the uncompressed mini header and also in the synchronization mini header it is essential to send the timestamp, but in the compressed mini header we do not send the timestamp. That means to say that the demultiplexer has to derive the timestamp. How? Using this time difference information and the last synchronization information. So time difference, then the RTP header, okay, and then the last synchronization information, and last synchronization information will contain as usual the sequence number, the context sequence, the RTP sequence, and the last synchronization's timestamp. So using the last synchronization's timestamp and the time difference ever since the last synchronization, it should be able to compute the current timestamp. Okay. So how it can do, okay, that will be clear from a particular example. So as an example, okay, let us say that the context mapping table in the mux that contains the following information at a given time. Okay. Supposing as an example, okay, we take up a particular moment, okay, where the context mapping table in mux contains the following information. Context mapping table in mux, okay. We are not bothered about all the fields, but fields with which we are most concerned, the CID, okay, this is equal to, let us say 10, okay. The context sequence number, let us say it is 2, okay, RTP sequence number, let us say it is 40, timestamp. Now this C sequence is 2, okay, this C sequence, mind you, is the C sequence of the last synchronization. So RTP C sequence, RTP synchronization, and the timestamp let us say is 14,200. So this is also from the last synchronization. So you see that we are referring to this information basically, last synchronizations, C sequence, RTP sequence, and timestamp. Its specific values are, let us say, 2, 40 and 14,200. Okay. And we now look at the demultiplexer. Okay. Context mapping in the demultiplexer, and say the context mapping table in DMARCS is like this. Okay. Say it contains the CID value, because CID has to be the same, since the session is the same, the CID has to be the same. Say the time difference is equal to 10. Okay. Then the C sequence is equal to 2, okay, and then the RTP sequence number, this will remain the same, that is equal to 40, timestamp is equal to 14,200. So these are all the last sync information. Okay. Now supposing that at this this time the multiplexer receives an RTP packet, say the MUX receives an RTP packet, now RTP packet has got an associated timestamp and the RTP sequence number. Mind you, it is receiving from the source, it is receiving the RTP packet. Okay. So it is containing the RTP sequence number and it is containing the timestamp, RTP timestamp. But now the multiplexer has to, when the multiplexer has to send this information to the demultiplexer, that time it has to perform a header compression, and in order to perform the header compression, it has to derive that what C sequence value is. Okay. So in order to derive the C sequence value, let us say that the particular RTP sequence number that the multiplexer has received is 43, okay, and the timestamp it has obtained is 14,230. Okay. Now this RTP sequence number of 43, okay, it has to, I mean, now it cannot send this RTP sequence number, but instead it has to send a C sequence to the stream, right. So now in the header, now in the compressed header, let us say that it is using a compressed header, the compressed header has to contain a C sequence value. Now what is the C sequence value that will be used over there? Okay. So in order to, so now the C sequence can be computed like this. So the C sequence value can be computed as the RTP sequence number, okay, the RTP sequence number in this case is 43, okay, minus whatever RTP sequence number was there in the last sync RTP sequence number. Okay, this is the current RTP sequence. This is the current RTP sequence is 43. The last sync RTP sequence number, which we know is how much? 40. Okay, and plus the last sync's C sequence. Last sync C sequence was having a value of 2. Okay. So that means to say that 2 corresponds, 2 in C sequence number corresponds to RTP sequence number 43. So 3 in sequence number contains RTP sequence number 41, like that. Okay. So that when it receives 43, okay, RTP sequence number, it knows that the corresponding sequence number for this, corresponding C sequence number for this has to be 5. That is very clear. 43 minus the last sync RTP sequence number is 40 plus last sync C sequence is 2. So that makes it 5. So, the C sequence number is 5. So, now in the header information, okay, what it gives is this value of 5. Okay. So, now in the header, so it can now afford to give a 2 byte header. In the 2 byte header, 4 bits will contain the CID, okay, CID in this case is 10, okay, and the C sequence, no sorry, C sequence value is 4 bits. So, C sequence value is equal to 5 in this case, and then the CID, right. So, now the demultiplexer receives this C sequence value, it does not know that what is the RTP header. So, when demultiplexer receives, okay, a C sequence value equal to 5, it has to accordingly reconvert the RTP sequence number. Okay. So, at the demultiplexer it can form the RTP sequence number easily. Okay. The RTP sequence number can now be obtained as the C sequence number that it has received, okay, minus the last sync C sequence number which is already stored. Last sync C sequence number is 2, and plus the last sync RTP sequence number that is also stored. Okay. So, it is 5 received now, the last sync was 2 and the last sync RTP sequence was 40. So, it gets back as the RTP sequence number 43, which was what the source was sending. Okay. Now, about the timestamp, now it has to recover the actual timestamp. It is 14,230, we know, okay. That is what the source had sent to the multiplexer, but multiplexer did not disclose that information. Multiplexer only says that your C sequence value is 5, but how the timestamp can be recovered? Well, you have the C sequence minus the last sync C sequence, So, the C sequence number difference, what is that? It is 5 now, okay. It was 2 in the last sync C sequence was 2. So, there is a C sequence difference of 3, okay. This needs to be multiplied by the corresponding time difference, okay. The time difference in the sequence is 10, okay. Now, the time difference is 10, so it is 2 into it is 5 minus 2 into 3, that means to say 30, okay, plus the last sync RTP sequence number is 14,200. So, it knows that the timestamp now should be 14,230. So, it recovers the timestamp, okay. So, we are sending less information, okay. The header compression definitely saves in lot of information, but essentially the usage of these context tables in both the multiplexers and the demultiplexers, okay, essentially that permits the multiplexer to derive the C sequence number, and from the C sequence number it enables the demultiplexer to get back the original RTP information. So, that is the trick that that is being done in this process of multiplexing, okay. Now, one point which should be noted is that initially, of course, the demultiplexer will not be having this information, okay. So, for the initial, so at the start of the session, okay, the first few packets, okay, they have to be sent in the fully uncompressed header type, okay. So, the first few packets will have uncompressed mini header, okay. Now, with that the demultiplexer will be able to find out that whether the fields in a particular session, which are the constant fields, and it will be able to find out that which are the fields that are changing, I mean that are having constant increments like the timestamp and the sequence number. So, accordingly it then I mean once those information are established, okay, from the next RTP packet onwards, okay, one can go through the one can then go through the RTP mini header compression, okay. Now, mini header compression you can do, but periodically you have to transmit the synchronization mini header. Why? Because you can see that C sequence number is only a 4-bit field. That means to say that after 4 bits, that means to say after 16, okay, the sequence number again roll over from 0000 if you start up to 1111, again it rolls back to 0000. So, I mean, since it is a 4-bit field, that is why once in every 16 RTP packets, okay, they have to be the synchronization, they have to contain the synchronization mini header, okay. And not only that, there are certain times, okay, there are like say for example, when an audio channel starts from a silence, okay, that there is a silence followed by some voice chunk is being sent, okay, there the synchronization information tends to lose, and that can be taken care by having the so that loss of synchronization can be corrected by giving forcibly the synchronization mini header. So, first few packets uncompressed mini header, then the regular packets will contain the compressed mini header, and periodically or when needed the synchronization mini headers have to be sent. Okay. So, this is the overall scheme that one goes through for the header compression. Okay. Naturally, I mean, compressing this to 2 bytes, okay, most of the times sending a 2 byte mini header, okay, is really quite efficient, okay, and in fact the efficiency we can calculate, okay, when we come to the formal way of calculating the bandwidth efficiency in the multiplex scheme, that we can indicate then. But before we go into that, okay, let us see that what is the call establishment protocol. I mean, we know that what sort of call signaling takes place in H.323, already we are knowledgeable about that, but let us see that how it can happen in a typical multiplexer demultiplexer type of scenario. Okay. So, for that let us say that we have an initiator, we have a station which is the initiator, and we have another station which acts as the acceptor, okay, and the initiator is connected to a multiplexer. Okay. Let us say that this is the multiplexer A. Now, incidentally, these multiplexers, they also act as gatekeepers. These are intelligent multiplexers, so these are acting also as the gatekeeper. So, in the total connectivity, we will be having the mux A, okay, and we will be having the demultiplexer correspondingly, which we call as B. So, in fact, both these things will be mux demux, mux demux both will be there, okay, because every such node will have the multiplexing and demultiplexing capability both. So, in this case, of course, since we are telling that this is the initiator and it is connected to A, and this is the acceptor and it is connected to B. So, in our case, A will act as the multiplexer and B will act as the demultiplexer. Okay. Now, how the sequencing will be made, okay, how the call setup will be made, okay, is like this. The initiator first sends an admission request. Admission requests, short form we write as ARQ. Okay. So, this is the step number 1. So, ARQ, this is the first signal, okay, that will be sent from the initiator to the mux A. Okay. Now, the mux A, okay, I mean admission request is there, but before having the admission confirmation, okay, the multiplexer has to find out, or the multiplexer has to locate the acceptor. Okay. So, what it does is that it broadcasts a locate request, okay, the locate acceptor, okay, by sending a locate request LRQ signal, okay, and this will be the step 2. So, the first step was initiator sending an admission request to the multiplexer, and then multiplexer sending a location request to this demultiplexer. In fact, it will be sent to all the demultiplexers to which it is connected. Okay. But the particular demultiplexer to which it is actually connected, okay, it will respond. So, supposing in this case B is connected to the acceptor, okay. So, the B will respond by saying that there is a location confirmation. So, it sends a signal, B now sends a signal called as LCF, which stands for location confirmation, and this is the step number 3. So, it comes from B to A. Okay. Now, the multiplexer knows that the acceptor has been located. So, once the acceptor has been located and it has verified the authenticity of the initiator, it sends an admission confirmation. Okay. So, admission confirmation or ACF will be sent as the step number 4. So, step number 4, the admission confirmation will be there. Okay. Now, once the admission confirmation is there, okay, then the endpoints can exchange the call signaling and the H.245 control messages. That is, as per the H.323, we know that the endpoint to endpoints, okay, there has to be a call signaling and there has to be a control negotiation or the capability negotiation through the H.245. Okay. So, that has to take place. So, that will be step number 5. So, it is for the signaling, and I am not giving any specific direction because actually it will be bidirectional, because the signaling will be coming back and forth. So, this is step number 5. Okay. Step number 5, where there will be, so step number 5 is for endpoints exchanging call signaling and H.245 control messages. Now, once the acceptor, okay, gets the call signaling, okay, acceptor has to now respond, and the acceptor responds by saying, by giving an acknowledgement signal. Okay. So, this could be in another dedicated channel which goes from the acceptor to the multiplexer. So, this is step number 6, okay, where it will be, step number 6 will be the acknowledgement from the acceptor. So, step number 6 is ACK. So, it is acknowledgement from the acceptor, and once the acknowledgement comes from the acceptor, okay, now the multiplexer and demultiplexer will know that now a session has to start, okay, because all the admission confirmation is there. Now, the call signaling has been initiated and the acceptor has also accepted that, okay, and acknowledged this. So, now it is ready. Now the voice packet has to begin, and before the voice packet transmission begins, okay, what the multiplexer and the demultiplexer has to ensure that this session has got a unique CID. Okay. So, now when in step number 6 it receives this acknowledgement, then a unique CID, the context ID, will be assigned to this session, okay, that this demultiplexer will do, and subsequently when this CID is assigned by the demultiplexer, that CID has to be communicated to the multiplexer also. So, now in step number 7, okay, we will be having the I mean that the demultiplexer that the multiplexer now gets, so the mux gets the, so acknowledgement from the acceptor, CID created in demux, CID created in demux, and not only the CID, but it also creates the table. Okay, the demux table is prepared. Now the mux gets the CID value and mux prepares the table, context table. And now once that is done, okay, then the initiator receives an acknowledgement from the multiplexer. So that is step number 8. So this is an acknowledgement from the multiplexer. The table has been created, CID has been assigned. Okay, now the actual voice packets can be sent. Okay, so then the actual voice packet transmission has to begin. So this is the setup sequence that will be followed. Okay, so now the important question is that why we are doing this, okay, and exactly what kind of a bandwidth efficiency are we going to achieve in this process. Okay, so let us see some performance analysis. Okay, with that, okay, so we will now talk about the performance analysis. Some quantitative measures are there for this. Okay, and the first performance analysis is what we call as the bandwidth efficiency. Now to do that, okay, we define the efficiency like this. Okay, so we call this as rho, okay, and we say rho with the multiplexer. Okay, in the multiplexed scheme, that what is the efficiency? The efficiency is measured as a ratio of the payload size. So that means to say that in the WAN domain, okay, so in the WAN means after the multiplexing is done, because the multiplex stream will be sent in the WAN. So in the WAN, the bandwidth efficiency or rho mux will be measured as the payload size, okay, upon the actual IP packet size. IP packet size again in the multiplex domain, payload size also in the multiplex domain. Now how to find out that? Okay, because how to find out the payload size? So we need some more information for that. Okay, what are the information? Okay, that's to say that what is the audio payload size? Okay, assuming that every channel or every mux demux pair or every source destination pair, okay, has a fixed audio payload size. Okay, audio payload size, and let us say that audio payload size is A. So normally we will be expressing this A in the unit of bytes, right. Okay, then say the number of voice streams that we want to multiplex, number of voice streams to be multiplexed, let us say that that is equal to n, that is equal to n. Okay, and now for every stream we have got a mini header, for every such n, okay, we have got a mini header, and the compressed mini header size is, let us say, HM, compressed mini header size, let us say that this is equal to HM in bytes. Now you can argue that all the mini headers will not be the compressed mini headers, some of the mini headers will be uncompressed, but that is at the beginning only, and some of the mini headers will be having the synchronization, that also we have to send periodically. So, but normally, okay, 99% of the mini headers or 90% of the mini headers will be of 2 bytes only. So, normally HM will be 2 bytes. Okay. So, that is the compressed mini header size. So, now tell me that what is going to be the total payload size in this row marks expression, what will be the total payload size given this information? A times n, because A is the audio payload size for every stream. For every stream the audio payload size is A, and we have got n such multiplexed stream. So, naturally this is A multiplied by n, that is the payload size. And what is going to be the IP packet size? HM is the mini header size. HM, the mini header has to be added with, mini header will be there in every stream, HM plus A. So, HM plus A becomes the complete size of a particular stream, okay, and there will be n such streams. So, HM plus A, okay, that multiplied by n will give us the mini header plus the individual payload and n for n such channels. But mind you, we are forgetting one more thing, that there is also an overall UDP header, because this has to be, this entire IP packet has to be sent over the UDP. So, there will be an overall UDP header which we call as the HUDP. So, HUDP is the UDP header. So, this will be our total bandwidth efficiency in the case of a multiplexed channel. Okay. Now, this is with a multiplexer in H.323. Now, if we do not have any multiplexer, okay, that means to say that a non-multiplexed method or the old method if we use, in that case the efficiency we can write as rho old. The rho old will be defined again as the payload size divided by the IP packet size. Now, when we are using the older methodology of non-multiplexing, there the payload size is going to be A, simply A, because we are not having n channels. I mean, all the individual channels are sent individually. So, A is the payload size, and what is the IP packet size? It will be the RTP header plus A. So, let us say that it is HRTP plus A, where HRTP is the RTP UDP IP header size, the RTP UDP IP header size. But mind you, this is very significant, okay. It is 40 bytes of information, no joke. It is 40 bytes of information is there in this RTP UDP IP header, okay. And let us see that what could be A, okay. So, if A is very large, then no problem, okay. But then let us say that we are using the state of the art codec. The state of the art speech codec is G.729, okay, and G.729, its bit rate is only 8 kilobits per second. So, if it is 8 kilobits per second, then considering the delays that we require, okay, to form a packet, the packetization delay will be very severe if we try to make our A very large, okay. So, given that actually the audio frame size in G.729, the audio frame size is equal to 10 bytes and the payload is made equal to one audio frame size. So, A is equal to 10 bytes. So that will really give us a very bad figure, okay, because with this figure the row old is going to be only 10, A is 10 and the RTP header is 40, 40 plus 10. So 10 by 50, that means to say 0.2, only 0.2 efficiency, 20% of efficiency is achieved if we are using the unmultiplexed thing, okay. But let us say that if we use the multiplexed scheme, okay, the expression that we had formed here, let us put some typical figures, okay, for that, okay. Let us say that HM in this case is 2 bytes normally, I mean taking the compressed header size, HM is 2 bytes, the mini header size. Then HUDP is pretty large, HUDP is 28 bytes, okay, 28 bytes. And supposing we have n equal to 45, say we have 45 multiplexed channels. So I think I specified everything else, okay. Our A is A can be taken as the 10 bytes as we had taken before. So A is 10, N is 45, HUDP is 28, HM is 2. So now let us calculate what is the rho max. Rho max will be equal to A into N. So 10 into 45, this divided by HUDP is 28 plus HM means 2 plus A is 10 and then we have got again N as 45. So it is 450 divided by 45 into 12 means it is 540, 568, right. So that makes it something like 0.7 or near about 0.8 roughly, 0.79, yeah, 0.79. So 0.79 is the efficiency, the bandwidth efficiency. So what it was only 0.2 in the unmultiplexed scheme, okay, and it goes up to 0.79, that is nearly 80% of the bandwidth is efficiently utilized, okay, in this process, okay. Now let us talk about the second performance analysis, and that is the capacity. So the second performance analysis is the capacity. Now in the capacity, basically the number of concurrent schemes that number of concurrent streams that will be possible, that will be given by this constraint, isn't it, that the aggregated voice data rate, that should be always less than the available bandwidth. Otherwise you will have packet loss, okay. So aggregated voice data rate has to be less than the available bandwidth, and let us say that the available bandwidth is B, okay. The available WAN bandwidth, we mean to say, is B, let us say, okay. And how to compute the aggregated voice data rate? Let us say that F is the audio frame size, and we have the mini header as HM. So HM plus F, okay, F is same as what we were calling as A, no problem. HM plus F into N is the number of simultaneous streams, okay, plus the header of UDP, okay. So this is the overall payload size, okay, that we will be having for n multiplexed streams, okay. And this is the payload size in bytes, but we now have to convert this into the bandwidth. So bandwidth will be actually measured in some bits per second unit. So, in order to do that, we have to multiply this by the data rate. So, if we calculate, so if we assume the G.729A codec, okay, having the 8 kbps of rate, okay, so there we will be having 8000, this multiplied by 8000, and supposing k is the frame period. So, k milliseconds, k in milliseconds is the frame period. Okay. So, now we can have that this into 8000 by k is less than b. Okay. So, this is the constraint, and in fact, if you take a typical figure of f is equal to 10 bytes, okay, you take k, the frame period, to be equal to 10, okay, and if you take the b, the bandwidth of the WAN link, to be 1.5 Mbps, okay, you can calculate and find out that the maximum number of n that we can achieve in this case is n maximum could be up to 153 streams. Okay. Whereas, if we do not, so this is with multiplexing. Okay. So, 153 streams we can have with multiplexing, and if we do not go through the multiplexing scheme, that means to say that in the old scheme there our rate would be slightly different. What it means to say is that the H.RTP, so they are the RTP header size, plus we have, let us say that R is the audio frame to packet ratio, R into F, because in this case we cannot have the audio frame to packet ratio to be equal to unity. So, R is the audio frame to packet ratio, because the packet has to be with smaller size, the packet cannot be one frame size. Only in multiplexed scheme we can have the packet equal to one frame size, but normally the packet is less than a frame size. So, audio frame to packet ratio, typically this figure will be less than unity. So, RTP, H.RTP the header, plus R into F, that times n number of channels, and the bit rate is 8 kbps, okay, this divided by again R into K, okay, this quantity will be less than B. So, this will be for non multiplexed. Streams, and you can see that using this figure we can have n max to be equal to 37 streams only. So, up to 37 streams can be accommodated in the non multiplexed manner, and using the multiplexer scheme 153, which is more than 4 times of the channels can be accommodated, more than 4 times of the streams can be accommodated using the H.323 with the multiplexing scheme. So, this is what I had to say about the H.323. Now, H.323 is a standard, I mean definitely it is a very useful standard that has been proposed by the ITUT. In fact, it is getting revised further and further, and very recently, even in June 2006, the last revision of H.323 standard was made. And H.323, although I have described it in the context of the voice over IP, but you will be surprised to know that H.323 can also support the video over the IP network. In fact, the I mean in the initial days of the video conferencing, because of the very high bandwidth requirement of the video and also the questions of the connection oriented protocols that should be used for the video. There the ISDN video conferencing was the first generation of video conferencing which was there, but more and more the ISDN video conferencings are getting replaced by video conferencing over IP. So, where video voice both has to be through the IP layer, and there the H.323 becomes a very efficient and powerful standard. So, for video conferencing H.323 is there, the SIP is there, and the SIP is the session initiation protocol, okay, and plus ISDN video conferencing is also there. So, in the next class onwards we will start with the video conferencing, okay, and we will see the ISDN video conferencing and the SIP protocol, because we are already familiar with the H.323. Okay. Thank you.